Good morning, ladies and gentlemen. I'm here today to talk to you about my ECTE451 topic, which was fault current limiters, and in particular the permanent magnet fault current limiter. Quick overview of today's topic. We're going to look at fault current limiters and their importance in modern electrical engineering. We're going to look at two types of fault current limiters. That's the saturated core fault current limiter and the permanent magnet fault current limiter. There are others out there, but these will be the two main focus of my research. Both the FCL models were generated in Flux, which is a finite element analysis software, and we'll have a look at both of those and a comparison of the results of their FCL's performance. So fault currents. These are short circuit currents which cause a spike in the amplitude of the fault current once it bypasses the load, essentially. They're occurring more frequently in present day. This is due to the ever-increasing loads that are being attached to the grid and the odd harmonics that are being fed back into the network from the renewable energy storage devices. Fault current limiters. They're devices that are implemented into power systems to help reduce these short-circuit currents. So they can bring the amplitude of the fault current down to protect such equipment as circuit breakers or transformers, which may have been originally built to not withstand such intense fault currents themselves. So reducing this short circuit current with a fault current limiter will help protect these devices and enable them to perform as they would have when they were originally built. Saturated core fault current limiter. So this consists of two AC coils in series. They're wound in opposite directions around the left and right limb to reduce both half cycles of the fault current waveform. We have one DC biasing coil within the circuit that is used to saturate the ferromagnetic core. So the flux is produced around both limbs and runs in a anti-clockwise or clockwise direction up from the DC coil itself. Once there is a fault current passed through the AC coils, there's enough flux generated within the AC coils to oppose the flux generated by the DC coil, and hence the permeability of the material will rise and the fault current will hence be reduced. Permanent magnet fault current limiter. This operates in the same manner as the DC, the saturated core fault current limiter, without the need for a DC coil. So the use of a permanent magnet, such as a neodymium magnet, is used to purely saturate the core magnetically instead of electromagnetically. And the same process of unsaturation once the AC coil receives a high enough spike in current. Here is the saturated core fault current limiter produced in the finite element analysis software, Flux. Here you can see you just generate a geometric Cartesian coordinates to generate a geometric model, and then the volumes are assigned to materials, so the software itself can calculate the results for the results for the flux density and the electrical and magnetic properties. Here we can see that the darker region, the dark grey black area, is your core. That was assigned to an M6 steel material. Our two yellow regions are our AC coils in series. These are defined by selecting a face internally and selecting a direction of current, and the circuit used for these will be seen later, and the DC coil in the middle is the green region. The region on the right is just the mesh generator. All the little nodes within this mesh are the calculation points which are ran once the scenario is solved. So permanent magnet fault current limiter, same concept. The green region is now a permanent magnet instead of that of a DC coil, and the mesh generator produces the similar mesh on the right hand side. Okay, here we have our testing parameters. The two circuits are our AC circuit on the top and our DC circuit on the bottom. So the DC circuit is only required in the fault current limiter for the saturated core fault current limiter, and the permanent magnet fault current limiter only requires the top AC coil. So we can see that our C1 and C2 represent the two AC coils on the left and right, and our DC coil C3 is represented here. So on the table on the left, you can see the testing parameters in which this circuit was, the parameters in which the circuit was tested. So under normal conditions, the top AC circuit just runs through the resistive load until a certain point in time the switch closes, which mimics a short circuit, and then the results from this can be seen within flux itself and the reaction of the device to these fault currents. So here we have just a little video of the simulation from the permanent magnet fault current limiter. So the arrows represent the flux direction, and the colour represents the flux density intensity within those limbs. So the left and right, so the flux density, goes from around 2 all the way down to 0 Tesla. So this is under normal conditions. You can see that both sides are saturated, and therefore these two appear as air inductors within the network itself. And then once a fault current passes through, one side will be unsaturated while the other gets driven higher into, further into saturation. So here we'll watch the video. So this is under normal conditions, and at 0.08, now we're starting to get into a fault current waveform with a positive half cycle. So this left-hand side is starting to unsaturate and come down into the darker region. So now the fault current passes through, and you can see the flux starts to head in the opposite direction, which isn't desirable, but that's going to be further studied in ECTE451. And then as the fault current moves into the negative half of the sinusoid, you can see that the left-hand side falls back into saturation, and the right-hand side of the core starts to be driven out of saturation. So this process repeats back and forth until the sinusoid current returns back to that of the same area as normal conditions, or same amplitude as normal conditions. So these results show that it is actually possible that elimination of the DC coil required for saturated core fault current limiters, it is possible to actually replace this and use just the purely magnetic methods to produce the same fault current limiting capabilities. Thank you for your time.